All right, we are on to a brand new unit. We have to go backwards a couple of chapters, back to chapter 7, lesson 1. For today's activity, if you want to have an actual calculator, not the one on your Chromebook, you could probably get away with the one on your Chromebook, but if you have an actual calculator, get it out. And if you still have the paper copy of your definitions, they should be in your science folder. Get those out as well. Because we are on to a new unit, that means we have to have a new set of goals. Our first short term goal is that you need to learn the factors of kinetic and potential energy. Factors are the things that give us more kinetic energy and things that give us more potential energy. Looking long term, our medium term goal for this quarter is to be able to describe the law of conservation of energy. Now, if you can think back to a couple of weeks ago, and if you can still describe the law of conservation of mass, I'm guessing you can pretty well guess what the law of conservation of energy is going to be. Then we're going to connect the two, and then both of these are going to come into play in the third and fourth quarter as well. Uh, the first vocabulary word that we need to work with is energy. The definition on your page is the ability to cause change or do work. We're going to get into what work actually is, but think about energy as being the ability to cause change of some sort, whether it's chemical or physical change. Of course, energy has units just like kilograms or liters or any other unit that we've been using. The most common unit of energy measurement of energy is in the form of joules, and you'll often see it as a capital J. So J for joules is our measurement of energy. All right. The very beginning of this lesson in the book, you're going to have a little question about an elevator and stairs, and it's asking which one has more power. Well, work, when we talk about energy's ability to cause change or do work, work is when a force moves an object. So an object has to move in order for work to be done. The power that you have to calculate is a rate. It's the rate or how quickly that work is done. So the formula that you are going to have to use is the energy transferred. So that'll give that to you in joules or newtons. And you're going to divide that by time. And you have to do a quick math problem about that. All right. The first main type of energy is potential energy. And if you look at your definitions sheet right now, potential energy is the energy stored in a substance due to its position. So, where the object is, or what the shape of the object can give an object the ability to cause change or the ability to do work. It's not necessarily moving. It's just because of where it is or its shape that it has energy, which is the ability to cause change or do work. The second main kind of energy that we're going to be talking about is kinetic energy. And if you have your definitions, you can look at that now. Kinetic energy is the energy a substance has due to its motion. So this is energy an object has because it is moving. It has the ability to cause change or to do work. All of the other vocabulary words that are on your page are going to fall under one of those two main categories. So if you look at thermal energy or chemical energy or nuclear energy or electrical energy, any of the energy vocabulary words, all of those are types of potential or types of kinetic. We have to work with two factors that can give an object more kinetic energy. So, kinetic energy, there's two things that can increase an object's ability to cause change or do work while it is in motion. And the first factor is speed, how quickly the object is moving. If you think about our definition of energy, it's the ability to cause change or do work. Um, If an object has kinetic energy, it's because it's moving. If it is moving faster, it can cause more change. Or if an object is moving faster, it can do more work. So an easy example is two identical tennis balls. If the top tennis ball is traveling at 10 meters per second, that's what the m/s is, meters per second. It's a speed. Um, it can do some work. Okay, it can cause some change. However, the same tennis ball at 50 meters per second is going to have the ability to cause more change. So at 10 meters a second, if I'm playing tennis against somebody and they hit a tennis ball at my face at 10 meters per second, when that tennis ball impacts my face, it's going to cause some change. It has energy. The same tennis ball hit at my face at 50 meters per second is going to cause more change to Mr. Bogdan's beautiful face. The second main factor is mass. The more mass an object has when it's moving, the more change that it can cause. Again, if we go back to our definition on energy, the ability to cause change or do work. If I have two objects coming at my face and one of them has more mass, it can cause more change. So a tennis ball traveling at 10 meters per second at Mr. Bogdan's beautiful face will cause some change. A bowling ball at the same speed, 10 meters per second, because of its mass, will cause more change to Mr. Bogdan's beautiful face. All right, so here's a quick brain teaser. We have a bowling ball and a tennis ball. They have the same kinetic energy. Which one is moving faster? You can pause. Okay. If a bowling ball and a tennis ball have the same energy, that means they are going to cause the same amount of change to Mr. Bogdan's beautiful face. So if a bowling ball and a tennis ball are going to cause the same amount of change to Mr. Bogdan's beautiful face, the tennis ball has to be moving faster to make up for its lack of mass. All right. You this week are going to have to calculate total kinetic energy. And there is a formula that you will see that looks like this in the book. It's 1/2 times mass times speed squared. And this little bit at the bottom, the 1 kg times m squared slash s squared, that's basically just telling us that we're going to be using our unit joules. Okay. So you're going to take 1/2 times mass times speed squared, and your label is going to be in joules. The key here is you're going to have to follow order of operations. So we're going to have to do the exponent first, speed squared, and then do 1/2 times mass times that answer. So here's a simple problem. Mr. Bogdan's cat, Hobbs, is 4 kilograms. He is sprinting around the house because that's what cats do from time to time. And he is traveling at 5 meters per second. When he turns the corner and hits Mr. Bogdan's leg, how much kinetic energy does Hobbs have? Well, the 4 kg, that's going to be our mass because mass is in kilograms, and our speed is 5 meters per second. So, using your calculator, you can do this now. All right. So, if we do the speed squared, that is going to be the speed is 5. So 5 to the power of 2 is 25. All right, not 10, 25. All right, so 1/2 times the mass, well, my mass is 4. 1/2 times 4 is 2. And 2 times my speed squared, which was 25. So 2 times 25 is 50, and that means 50 joules. So Mr. Bogdan's cat is going to have 50 joules of energy as he's running around the house because of his mass and his speed. All right. So, well, there we go. All right. So Another calculator problem. So Carlos Dunlap, who at the time I'm recording this just got traded from the Bengals like 2 weeks ago. Carlos Dunlap played for the Cincinnati Bengals, and he has a mass of 127 kilograms. He can also run 7.6 meters per second. How much kinetic energy does he have when he tackles someone? And remember that my cat running around had only 50 joules. So my speed is 7.6. You're going to have to do that to the power of 2. And then do the 1/2 times 127, and then times 7.6. If you have a calculator, you can pause now and quickly figure this out. Okay, so 7.6 to the power of 2, and then 1/2 times 27 times that answer, you should get 3,667.76 joules. And if you're confused about how to get that, just raise your hand and Mr. Bogdan will help you. All right. The second factor is potential, or sorry, the second energy we have to investigate is potential energy. In this book, in this lesson, there are two types of potential energy. There's gravitational potential energy, and then there's something called elastic potential energy. Let's take a look at gravitational potential energy. That has two factors. We can see them right here on the screen. They are weight and height. Weight is going to be measured in a unit called newtons for us. So we're going to look for the newtons number when we're trying to identify which number is weight. And then height, that should be in meters. All right. So if I have two bowling balls, if I can get one to load, and that one's not going to load. There should be a bowling ball right there. There we go. Um, if I have the same bowling ball at two different heights, well, its weight is the same, but a bowling ball dropped from 4 meters is going to cause some change to the ground, and the same bowling ball dropped from 6 meters is going to cause more change to the ground. That's because it had more potential energy. So, how high something is off of the ground is a factor of gravitational potential energy. The higher it is, the more gravitational potential energy it will have. Now, if the heights are the same, then weights are a factor. So here we've got a tennis ball and a bowling ball. They're at the same height, but they will cause different amounts of change to the ground. A tennis ball dropped from 4 meters because of it doesn't have a lot of weight, won't cause very much change to the floor. A bowling ball drop from 4 meters will cause a lot more change to the floor because it's just got a lot more weight, even though it's at the same height. All right. So, another sample problem. Which one is going to have more gravitational potential energy? So, there's my cat Hobbs, who is 4 kilograms, which is approximately 40 newtons. Now, newtons is my weight. You're going to ignore kilograms because that's mass. So, 40 newtons. He's sitting on the back of a couch. That's a height of 1 meter. My other cat, Catorze, is 90 newtons. Yeah, he's more than twice what Hobbs is. My other cat, Catorze, is 90 newtons, but he's sitting at a chair, so he's only got a height of half of a meter. So one's got more weight, but is lower to the ground, and the other one's got more height, but is lower in weight. So plug those two numbers into our formula, weight times height. 40 times 1 and 90 times 0.5. Which one's going to have more potential energy? You can go ahead and pause and figure those out. I'm going to continue on. All right. So Hobbs, 40 times 1 is 40 joules of gravitational potential energy. Catorze has 45 joules of gravitational potential energy. All right. Just as a heads up, as you if you come across any videos like on YouTube or wherever, they may give you the formula that gravitational potential energy is mgh, mass times gravity times height. Weight, which our book is using, has already combined mass times gravity. And that's what weight really is. It's an object's mass times the gravity system that it's in. On Earth, the gravity is like 9.8, I think is the number that they use. So it'll be an object's mass times 9.8. Anyway, weight times height and mass times gravity times height are the same formula. All right. The last section in this lesson is going to be about elastic potential energy. And that's the kind of potential energy an object has due to its shape. And that's when an object's shape has been compressed or stretched. So um, here's a spring in its normal position. If you compress it, you've given it elastic potential energy by compressing it because it wants to go back to its original shape. So it's sitting there ready to do work or ready to cause change because of its shape. If you stretch a spring, it's also going to want to go back to its normal shape. So by stretching it, you've given it elastic potential energy because it wants to do work and go back to its original shape or original position. If you think about something like a bow and arrow, when you pull back the string, you are stretching it. You're stretching actually the bow. And so the bow has elastic potential energy and it wants to return to its original position. And then that will cause the arrow to have kinetic energy. All right. You need to read pages 236 to 241, answer all the questions, and good luck to you.